Hi. Okay, now we're going to look at the conservation of energy. Let's take a look at the equation on the board, shall we? Basically what this is saying is the total amount of energy that you have in a system before some event must be equal to the total amount of energy that you have in the system after the event. Let's look at the different forms of energy. This is MGH, or potential energy due to height. We would more traditionally call that gravitational potential energy. This is 1/2 mv squared, which is kinetic energy, or energy due to something moving. This is 1/2 kx squared, where k is a spring constant, x is the distance that a spring has been stretched or compressed. That's the potential energy stored in a spring. Now on this side of the equation you see prime. Now I don't want you to confuse prime with what you see in calculus, meaning the first derivative of a variable. This prime simply means final. So I just as easily could have said mgh sub f or h final, but it just really depends on the book that you've learned it from, and I came from the school of where we would call that prime. So mgh, this is potential energy due to height, prime or final, 1/2 mv squared or kinetic energy final, and then 1/2 kx squared prime, where x squared prime is again the distance that it's compressed or stretched, and that's the final position of that spring. Now here's the strategy that you use to solve these problems. What you want to do is look at the case before, or in the initial conditions, because when you look at the initial conditions of the problem, you actually will be able to simplify this half of the equation and lose some of your terms, depending on the problem. Then you will look at the final conditions and eliminate some of those terms so that you have the equation that you're going to use to actually solve the problem. Let's do an example. Let's just say a traditional conservation of energy problem is a roller coaster. So let's just say that we have a roller coaster that's 100 meters high from the ground, like this. And here's the roller coaster cart up here. Like that. And the roller coaster is going to come down the hill to here. Now here's the beautiful thing about energy. It's a scalar, which means it only has magnitude. So we're not going to have to break this into the x and y components like in the 5 steps. We can just deal with the magnitudes. So the problems tend to be a little bit simpler. So the first thing we do is we look at our initial conditions. What are the conditions of the problem before anything happens? Well, it's sitting on top of a hill and it's not moving yet. So we go down the line. Does it have potential energy due to height? Yes, it does. Is the object moving yet? No, it hasn't started to move down the hill. So it has no kinetic energy. Is the cart in contact with a spring? Not yet. So it has no potential energy due to a spring. So that simplifies the left side of the equation to mgh. Now let's look at the final conditions. When the roller coaster gets to the bottom, of course it will have sped up. So now it's converted all of its potential energy into kinetic energy. So we can now look and see that it has no potential energy because what is its H value when it's down here? It's 0. So it has no potential energy due to gravity, but it is moving. So it has 1/2 mv prime squared, and it's not in contact with a spring. So it has no potential energy due to a spring. So now this simplifies to 1/2 mv prime squared. Well, the first thing that you'll notice is The same mass that was up here, which is the mass of the cart, is the same mass down here. So these two masses cancel. That leaves you with GH equals 1/2 V prime squared. We're solving for the velocity when it gets down to the bottom, so we bring over our 2. Because if I take the square root of both sides, the square goes away. Now you have your velocity. You have the velocity of the cart once it gets to the bottom. Pretty simple, huh? Roll this back and try the problem on your own. Go through the problem, look at the initial conditions, and systematically simplify your equation till you have the equation that you're actually going to work with. Then solve for the variable that you want. After you get the variable that you want, now plug in your numbers and get your final answer.